So folks, I've had a couple of you ask me about this question here. This is from our MyLab Math, and for fall 2022, I believe this is our question number 21, but for anyone else referencing it, this is from section 15.4.43. That's the reference number for this question. And in this case, we've got a function f, which is a function of two variables, each of which are functions of two variables. And so this is a chain rule sort of problem. That's why it's falling in under the 15.4 section. And somewhat different here, folks, we are asked to find a second derivative using the multivariate chain rule. And so this is what's challenging about this question. So just like we've done before, we can go ahead and take our function f and write it first in terms of its intermediate variables, and then write each of those intermediate variables in terms of their independent variables. And so if we want to find f sub s, let's first find f sub s using the multivariate chain rule. Hopefully we feel comfortable with the idea of saying, okay, we'll look at the paths that we can take down to s and construct the chain rule that way. If you have any questions about that idea, let me know. Now, what I'm going to do here, and it's kind of hinted at in this question, I'm going to keep everything in terms of this subscript notation. If you try to use the Leibniz notation, I found that this problem just got a little too unwieldy, and it's a lot easier to use this subscript notation. So this will be f sub x, x sub s, plus f sub y, y sub s. So again, we take the partial derivative with respect to x, multiply that by the partial derivative of x with respect to s. That's what I did here. Then we took the partial derivative of f with respect to y and multiplied that by the partial derivative of y with respect to s. That's how we got the first derivative, first partial with respect to s. Now we get to the challenging part of this question where we want to take the derivative of that again. So let's go ahead and just start setting it up formally. So if I want to take f sub s, I'm going to take the answer from above. And folks, I'm trying to use capital X's and capital I's just so I don't get my subscripts confused with the actual letters themselves. There's no actual reason to do that other than bookkeeping. And so what I'm going to do now is I'm going to apply the partial derivative with respect to s to this expression here. So the first thing we note is that the partial derivative distributes over sums of functions just like the ordinary derivative did. So that's all I'm doing there is saying I'm going to take the partial derivative of each of these two terms. And then I want to distribute this partial derivative operator over this product. Notice that's a product, but I'm going to have to use the product rule here. So this is going to get a little more lengthy now as I try to write this out. So how do I do the product rule on this? I'm going to do the derivative of the first, so f sub xs times the second, plus the first, f sub x, times the derivative of the second, times x of ss. And all of that, just to clarify, is this product rule right here. Similarly, on the right-hand side, we've got, oops, I don't want that to be red. We want to take this derivative here, so I'm going to do a product rule again. So I'll take the derivative of the first, leaving the second factor alone, plus the first factor, leaving it alone, times the derivative of the second factor. Again, all that's with respect to s. So all of this is this expression here. Careful, folks, this color coding has nothing to do with this color coding over here. Okay, so if we look at our givens, which of these are we ready to compute? Well, for example, I have x, and so I can find x of s, and then once I've got that partial derivative, I can take the partial derivative again, so I'm good to go with those. I can compute partial derivative of f with respect to x. That's just taking that partial derivative. And a lot of these other partial derivatives are ready to go. The ones that aren't, the two challenging ones that we still need to compute, are this one right here and this one right here. We don't know, we don't have expressions for those just yet. So while you don't have to do this, what I'd like to do is create new tree diagrams. Here I've got this function f sub x, and I want to take the partial derivative of it with respect to x, or excuse me, with respect to s. So let's try that. There's my f sub x, and if I want to take its partial derivative, I'd have to create a chain rule tree just like we've been doing. And so this is why I'm saying you don't actually have to do this, because notice that this tree is identical to this tree. But the difference is I'm not taking the partial derivative of f with respect to x. I'm taking the partial derivative of f sub x with respect to s. So what I can do now is in place of this statement here, f sub x of s, I'll go ahead and compute that. So all of this is going to be, for this green section right here, we've got f sub x. So the one way I could trace this down is go this way to here. So that's f sub x of x times x of s. That's that path there. Plus, how else could I get there? Well, I could take this path down. So that's f sub x y times y sub s. So all of this here is just the f sub x of s right there. So then I'll just copy everything else over. X of s plus nothing special to do here because all of these I'm ready to compute just having been given these statements. And then I get to this part right here, also in green, that I need to work on expanding. So what we'll do here, and again, you don't actually have to write a separate tree, but I think that it organizes your thoughts a little better. And so we're going to take f sub y sub s. So there's f sub y, oops, that should be red. There's f sub y, and how can we get to s? We can go down this way, or we can go down this way. And so I'm going to expand this f sub y sub s right here as plus f sub y x, x of s, plus f sub y y, y sub s. And folks, I apologize, I have bad allergies, so this video is going to be a little bit sniffly. I'm sorry. So all I've done here is expanded this, oops, that should be green, this f sub y sub s right here. Everything else we just copy over, y sub s, plus f sub y, x of ss. And at this point, although we've got this huge mess, what we have is a formula now for computing f sub ss. And now all we need to go and do is compute each one of these individual partial derivatives and plug them into the formula. So what we'll need to do is we'll take our f sub xy, which is our 2x squared y, and let's compute all these partial derivatives. So if we do f sub x, that would be 4xy. If we do f sub xx, that would be 4y. If we did, let's give ourselves a little more room. If we did f sub xy, I think we need that. Yep, right there, we'll need it. So if we did f sub xy, that would be 4x. And if we do f sub y, and etc., we'll just fill these in. So f sub y would be 2x squared. F sub yy would be 0. F sub yx, we can either compute or we can use Clairaut's theorem and say that's 4x. Likewise, we've got our expression for x in terms of s and t. There we have x. So let's give ourselves a little more room here. We've got x is equal to 2s plus 2t. So we'll need x of s, that would be 2, and x of ss would be 0, x of st would be 0, our x of t. Actually, we don't need to compute those for this particular problem. We'll go ahead and fill it out just for completion's sake, though. X of t would be 0, and x of ts would be 0. And then we've got our y, which we've said is s minus 2t. So if I compute y sub s, I get 1, y sub ss, I get 0, etc. If I compute my y sub t, I get negative 2, y sub tt is 0, and y sub ts, I also get 0. We're lucky in this case, folks, in that a number of our derivatives are 0, and that will greatly simplify this next part of the problem. So what I'm going to do now is I'm going to go back to this formula that I constructed at the beginning of this video, and I'm just going to plug in all the pieces. For instance, f sub xx we said is 4y times, and we'll need a bracket there, times x of s, which we've said is 2, plus f sub xy, which is 4x, times y sub s, which is 1, all times x of s, which is 2. And we can clean up that expression. If you want, you can fill in this expression. We have f sub x, which is 4xy, but we're going to multiply that in this case by x of ss, which we've said is 0, plus and then we're just filling this out. So I'm just going to go ahead and fill this out quietly, and I'll let you try it yourself. And so now if I go ahead and clean everything up, I end up with 8y plus 4x times 2. That zeroes out. I'm left with a 4x times 2 times 1, and those other parts zero out. So it leaves me with 16y plus 8x plus another 8x. So 16y plus 16x. Now, in this case, we've got expressions for y and x in terms of s and t, so all I'm going to do now is plug in the original functions. X is this function, y is this function, into these statements here, and that's probably as far as I'll take it. So this will give me 16 times s minus 2t plus 16 times 2s plus 2t. And I know I said I wouldn't simplify it, but just looking ahead, I see that some t's cancel. So let's call this 32s, and then I'd have a minus 32t plus 32t. So that's what I end up with for my solution. Oh, sorry folks, I have an error in simplifying that. That would be 16s plus 32s, which is 48s, the solution here. So then I could find other partial derivatives as well. And this is a tedious problem, folks. Give it your best shot. Let me know what your questions are. But all I've done so far is find f's of s. I would need to come up with similar formulas for s of st and f's of tt and f's of ts, all using this subscript notation. So if I could just review what was challenging about this. Here again, as always, the tree diagrams were key to being able to compute these partial derivatives using the chain rule. So I use this tree to first come up with f's of s, and then I am just asking myself to take the partial derivative of that again, in this case with respect to s, because I want to compute f's of ss. I distribute that s partial over the sum. In blue here, then I've done a product rule, and in orange here, I've done a product rule. And then to me, I feel like kind of the hardest step here was recognizing at this point, I'm asking to take the partial derivative of the function f sub x with respect to s. And that's where I went and constructed a new tree. You actually don't need to construct a tree, you just need to trace the old one the same way. But I went ahead and constructed that new tree, and how did I get this green expansion here? I got it using the chain rule on this tree diagram. Likewise, over here I did the same thing for f's of y. I hope that helps, folks. Let me know if you have any questions on that. This is a tedious problem. Give it your best shot, and I will see you in class.